Yeah, technically really good. Sorry. Oh, I think it's water.
All right, then welcome back, everybody, to the second morning session. It's my great pleasure now to have Michael Newman from Google with a talk on halving the cost of surface codes.
Perfect. So hopefully everyone can hear me okay. For those of you who don't know me, my name's Mike. I'm a research scientist at Google. And today I'm going to be talking about halving the cost of surface codes by running error correction at the logical level. And this is based on an arXiv paper that we put out a few months ago called Yoked Surface Codes. And it's a very timely talk, I think, because Stephen was sort of taking the surface code to task in our last talk. So as of 5 minutes ago, I've renamed my talk, The Surface Code Strikes Back, at Stephen specifically, after being ruthlessly slandered. But no, more seriously, I agree with everything he said, and you'll hear a little bit more about that in this talk. And before I get going, I'll mention that this is joint work with 3 of my colleagues at Google, specifically Craig Gidney, Peter Brooks, and Cody Jones. So like I said, you heard really quite a lot about this from Stephen, but why do we like the surface code? What are the nice properties that it has? And the 2 things that I really want to focus on for this talk are it can be implemented very nicely in a 2D nearest neighbor grid, like a square grid, for example, and it can tolerate very high error rates. Right. One of the reasons that the field kind of moved from concatenated codes to surface codes was because we saw in the surface code you could tolerate error rates up to about 1% and be below this magic number that Stephen mentioned called a threshold. The bad, as you've seen, is that it's very, very qubit expensive. So for the fault-tolerant algorithms that we think we need to run in order to see sort of a quantum advantage, it might require trillions of operations. And to successfully implement trillions of operations at a physical error rate of about 10 to the minus 3, which is where we think we can comfortably get to, it's going to require more than 1,000 qubits per logical qubit in order to build these surface codes with low enough error rates. That's very expensive, right? This is a distance 22 surface code on the left. It's coming up on 1,000 qubits. If every one of your logical qubits looks like that, it's going to be tough. So what do we do? Well, as you've seen, one of the things we can try to do is build long-range connections. And the reason that we want to do that is because there is this sort of no-go theorem that was proven by Bravipool and Terhall way back in 2009, which basically says that if you have a 2D nearest neighbor error-correcting code, purely in 2D, there's kind of a bound on how efficient it can be. Namely, the number of logical qubits k times the square of the distance is going to be O of n. And so the surface code family, as you increase the distance, actually saturates this bound. So in that sense, the surface code is kind of, saturating some no-go theorem. Now you could try to build long-range connections, and we've seen a lot of really nice work from neutral atoms groups and superconducting groups. But it is for certain architectures a lot simpler to build kind of nearest neighbor connections. And so a natural question that you might ask yourself is the surface code really the best solution for a low overhead quantum memory in 2 dimensions? And the answer is, and in my opinion, is no. And we kind of know this already from this nice work by Pattison, Krishna, and Preskill down here, where they were focused a little bit more on the asymptotics. This talk is going to be focused on, I actually have a target logical error rate I want to hit, just 1 in a trillion error rates, and what is the actual space-time overhead that I require for hitting a memory that can preserve information for that length of time, rather than seeing some sort of asymptotic advantage. And the idea is actually pretty simple. So suppose that you had qubits that failed with error rates of, let's say, 1 in a million. Would you use the surface code? I would argue no, because as we heard about in the last talk, it's relatively qubit inefficient, right? The surface code's strength is that it can tolerate really high error rates, but in terms of efficiency, in terms of qubit overhead, it's not very good. So what you can do, the way that you can think about this is, well, let's say that I'm building a surface code and I'm building it larger and larger. At some point, that surface code is a 1 in a million error rate qubit. And at that point, I shouldn't just keep increasing the size of the surface code. I should use a different error correction scheme altogether, just like I would for any other 1 in a million error rate qubit. And so the idea here is that instead of increasing protection by continuing to extend the surface code, we can increase protection by running error correction, some more efficient error correction at the logical level. And more specifically, what we're going to do is we're going to encode information redundantly using many low-distance surface codes instead of just making really big surface codes. And we're going to measure this information, this non-local logical information, by using measuring these parity checks using lattice surgery, which you heard a little bit about in the last talk, but is an entirely local operation. So what kind of error correction are we going to run at that top level? Like, what is this efficient error correction? Well, let's do the absolute simplest thing, right? Let's use what we call the n-2 code. It's an error detecting code. And for those of you who aren't sort of quantum error correction people, you can think of this as the quantum analog of basically appending a parity bit to a register of bits. And this parity bit should always be equal to the parity of the other bits in the register. And when it's not, for example here, it tells you that an error has happened. And so the n-2 code is exactly doing this, but now you need two parity bits. You need a parity bit for the x basis information, and you need a parity bit for the z basis information. And the information is just encoded. For example, the information encoded in this qubit here, if you wanted to probe the z information about that qubit, you would measure this z operator on this qubit, as well as a z operator on this z parity bit. So we're just encoding the information with extra parity bits at the logical level. And on the right-hand side here, we have a list of the logical operators where you can kind of see these are the y logicals from which you can get these x and z parities, these x and z logical parities. And you can see how information is kind of encoded. One kind of bit of information is encoded in each of these bits, but then it's spread out over these two bits as well. So I mentioned that the title of this paper was Yoked Surface Codes. I'll come back to where that name comes from a little bit later. But what these yoked surface codes are exactly what we've kind of building up to. It's simply a concatenation of what we would call a rotated surface code into one of these error detecting n-2 codes. So visually what this would look like here is like instead of every dot representing a qubit, I have a surface code. Instead of measuring, this blue object here represents an x-type stabilizer, so an x stabilizer on all of these qubits. And blue represents a z-type stabilizer, and red represents an x-type stabilizer. Blue is z, and red is x. And instead of measuring physical 8-body z-type operator here, or x-type operator, I'm going to measure a logical 8-body x-type operator. So instead of measuring just individual x-type on these single qubits, I'm going to be measuring these strings of x-type operators on these surface code patches. Now, the way that I do that is, again, through lattice surgery, which you heard a little bit about in the last talk. So let's just go through kind of a lattice surgery 101 example. So here is an example of one of the smallest error detecting code, the 422 code. So I have 4 code patches, and I'm encoding 2 bits of information. And let's see how I would measure one of these 4-body z-type operators, logical operators. So what I would do is I would first extend the lattice into some ancilla space, right? You're measuring a stabilizer, so you need some notion of an ancilla. And the way that you would do this, you would prepare all these qubits in the red basis, or in this case, the x basis. I would start just doing my normal syndrome checks, so just average, everyday sort of error correction, like what you would run if this was just a normal surface code. I wait for some amount of time to sort of learn information about what these parity checks are. We'll talk about why in just a second. And then at some point, after I'd gained confidence that I'd measured enough times, I would shrink this back down by just measuring all these qubits in the x basis, or the red basis. And then the only active qubits I have left going are these 4 surface code patches. Now, what I've learned here is exactly, assuming that I've done this enough times to be confident that I have the right answer, I've exactly learned I can look at the product of all of these blue stabilizers here, right? All of these z stabilizers. And if I look at their product, any qubit up here is kind of canceling out. You can see like every qubit here cancels with these 2 stabilizers. But their product is the product of these 4 z-type logical operators. So by doing this, using only local checks, I'm inferring the value of a logical parity check, which is this 4-body z-type logical operator. So how does the scheme work at a really high level? It's very, very simple. We let our surface codes kind of go on their way, do whatever they want to do. And then every so often, we're going to, if there's an error in one of the surface codes, which would be represented by a logical string that traverses the lattice from top to bottom, we measure one of these checks. We call these yokes, and we call these yoked surface codes. Yokes coming from like the yoke of an oxen, allowing surface codes to kind of distribute the work among them. And we'll catch this error. I won't talk about how we'll correct it until a few slides, but at least we're catching it. Again, if there's an error on one of these other surface codes, we at least catch it. But if there is an error on 2 of these surface codes at the same time, well, then we won't catch that error. That will corrupt our logical information, and we will be none the wiser. But you can see how this is doubling the distance of these codes, because you need twice the distance number of errors in order to corrupt the information. Now, at this point, this might sound really quite simple. And it is. It's a pretty simple idea. But there's a few sort of nice properties of the surface code that make this really, really efficient. And it really comes down to the observation that the surface code, while being expensive, is a really, really great qubit. It's a really great starter qubit. You know, we're paying all this overhead for this surface code. For example, let's say the inner surface codes were distance 10, so 200 qubits. So we want to get our money's worth in taking advantage of all of its nice properties. So the first property that we can take advantage of is what we call soft information. So let's say I'm running my logical error correction, and one of my parity checks says something bad has happened. You know, ostensibly, I don't know what what surface code has sort of gone wrong, but I'm certainly not going to throw out my information. So what I can do is I can actually inspect the surface codes. I can say, okay, well, these red dots represent syndrome flips, like places where an error has happened nearby. And I can say, well, these 3 surface codes look totally fine. I'm not too worried about an error on any of these 3, but this surface code looks very, very suspicious. And so I can sort of find the most suspicious candidate by inspecting this lower level information. And then from that, I can choose which of these surface codes to kind of flip back where I think the error has happened. So very briefly, for the sort of more error correction inclined in the audience, the way that we actually do this is by computing something we call the complementary gap. So this is kind of a picture of a surface code error graph. The nodes are these locations where you can have these syndrome bits. So the red dots represent places where the syndrome bits indicate there was an error. And the way that minimum weight perfect matching works is it kind of chooses the most likely error given this set of syndrome bits. So on the left-hand side here, we have the minimum weight perfect matching would be these red edges right here. And sort of connect up these syndrome bits that have indicated an error. We can also look at something called the complementary matching. And this is kind of like the most likely error that's not the minimum weight perfect matching, but kind of has the opposite effect on the logical information. And in this particular picture, the blue lines would represent this complementary matching. And now if I look at the log likelihood ratio of these 2 numbers, it gives me basically a confidence of how much I think that, you know, how confident am I that my error correction was correct. So for example, in this particular picture, I can represent this in decibels, for example, and I can look at the, you know, what was the likelihood of the minimum weight perfect matching versus the complementary matching, and this gives me an estimate that probably I was right. I would only have been wrong 1 in a trillion times, which is very unlikely. Whereas on the right-hand side here, the minimum weight perfect matching is this blue line. The complementary matching would be this red line. And if I look at the gap here, this I would estimate that I would only be wrong 1 in 1,000 times. So if I saw these 2 things and one of my logical parity checks told me there was a problem, I would definitely choose the right-hand surface code as kind of the likely candidate for error. And I want to mention there's a nice paper, I think, coming out by Pattison and others that exactly looks at sort of computing sort of a similar quantity a lot more efficiently. And I'll come back to this a little bit later. The second ingredient is that, well, we need this whole thing to be fault tolerant, right? We can't just ignore fault tolerance at the logical level. And so, you know, one of the nice properties of LDPC codes that I think we kind of talked about a little bit in the previous talk is that, you know, they're really good at not spreading correlated errors too much. We are using absolutely not LDPC codes here, right? This is an n-2 code. It couldn't be less LDPC. The stabilizer is literally the weight of the whole thing. The weight of the stabilizer is the entire code block length. So in particular, let's look at how we can make sure that this logical error correction is fault tolerant. And so I've kind of drawn a picture here where basically the physical picture, for every physical error you might have, there's some corresponding logical error. So if you're familiar with sort of a surface code stabilizer, this would be measuring as a 4-body Z-type stabilizer on the surface code. Let's look at how the errors that show up on the left-hand side here kind of manifest on the right-hand side and how we can fix them. So the first error would just be, let's say, an X operator on one of the physical qubits. And this is represented by an X operator that happens, a logical X operator, that happens on one of the surface code patches, right? And of course, we will detect this with this yoked check. And this is exactly the sort of error that this error correction scheme was designed to check. So everything is good here. So logical Z-type stabilizer measurements catch logical X-type errors, just like Z-type stabilizer measurements catch Z-type errors. We can also have measurement errors, which in this context would be some string of sort of a stabilizer measurement going wrong. And that corresponds to an error over here, which will just commute through these C0 gates and will just give you a wrong measurement result. And that's why we have to repeat these stabilizer measurements very many times to gain confidence that we're getting that measurement correct. The final one, so fault-tolerant measurements repeated many times will avoid logical measurement errors. The last one, which is the dreaded hook error, right? And this is why designing fault-tolerant circuits can be such a pain. You can have an error on the ancilla qubit that propagates through the C0 gates back to the data qubits. And it can propagate and hit many data qubits at once. And the corresponding error on the right-hand side would be a string of Z-type operators that sort of propagate from one side to the other of this ancilla block. And the way that you can see that this is equivalent to two of these Z-type physical operators is I can shift this operator by multiplying by stabilizers. So if I multiply by all the stabilizers on the right here, I can see that this operator is equivalent to these two logical operators on the surface codes. This is really bad, right? This is really bad for logical error correction because this is a single error that is causing two logical errors. And so this would kind of defeat the purpose of running logical error correction in the first place. This would be my dominating error. So we need to find a way to get rid of that. But the surface code is really handy, right? The surface code allows you to dynamically bias yourself away from certain errors by extending it in the direction of that error. So for example, one thing that we could do is we could just, while we're doing these checks, which happen infrequently, we could actually bias the protection against these non-fault tolerant errors at the logical level by extending the lattice so that this error happens below whatever the noise floor is that we want to realize out of our logical error correction scheme. And actually, if you're a little bit more clever, and if you're interested, so if you're familiar with topological diagrams, this will make sense to you. If you're not, just kind of listen to the soundtrack. Another thing is that when you're doing lattice surgery, you can trade space and time essentially interchangeably. So what you can do is instead of doing this kind of lattice surgery, just this longer lattice surgery to avoid this hook error, you can reorient your lattice surgery so that this hook error is not oriented in space, but it's oriented in time. And then once it's oriented in time, you actually don't even have to make these surface codes any larger. Uh-oh. All right, well, you don't have to make these surface codes any larger. You just have to run error correction, these syndrome checks for a longer period of time to kind of get this extra suppression against these hook errors. And that's really nice. It's not a free lunch because if you run these cycles for longer, the error is kind of increasing. But it turns out that it's a nice trade-off that causes us to not have to use these extended surface code patches. So everything is really being done in these small surface codes, which is nice. The final sort of ingredient that we can use is a really simple one. It's that if I'm actually measuring these surface codes, if I have a code block, and I want to measure using this ancilla block, these X and Z type stabilizers, that's doubling my overhead, right? Like I have literally a block that is the exact same size as the code block, and I'd really like to get rid of that. But surface codes have really low error rates if you make them large enough to begin with. And so maybe I don't have to measure these logical checks very frequently. Maybe I can measure them infrequently and then share some logical block, share some workspace between many blocks of these NN-2 codes. So on this picture here, here these white squares, all these squares are surface code patches. Every row here is its own individual surface code, like NN-2 block. So on the right-hand side, these gray squares correspond to an overhead, which are the X and Z parity bits for that block. And on the bottom, we have this workspace, which is basically this ancilla workspace that an adjacent block can use to measure its logical stabilizers. And so what I can do is I can say, well, initially, my workspace is right below this first row check. And so I can say, OK, well, this initial row is just going to measure its X and Z type logical operators, and then it's going to pass the buck. It's going to pass that workspace to the next logical block, which will then measure its stabilizers and pass it up to this third logical block, and so on and so forth. And so we're only measuring these checks infrequently, but if the error rates are low enough, this is kind of acceptable. Now, if I think about what the overhead of this scheme is, the number of logical qubits I'm encoding is the number of white patches here. And this perimeter of these yokes in this workspace, that's kind of the marginal overhead that I get by using this scheme. And what it buys me is doubling the distance of protection here in these surface codes. So if you actually think about it, if I make this block taller and I make this block wider, right, because the number of logical qubits is scaling with the area and the overhead is scaling with the perimeter, the overhead, the marginal overhead is going, the relative overhead is going to 1. Which is a really nice property to have. So as a code family, you could kind of think of this as fixed distance, but kind of rate 1. Now that sounds great, but obviously there's some kind of caveat. We can't just make this thing bigger and bigger and it gets better and better. The caveat is that as we make these blocks wider, the parity checks, the parity bits, are responsible for more and more surface codes. And as we make them taller, there's a single workspace that's going to be shared among more and more blocks. And so those blocks are going to be able to measure these stabilizers less and less frequently. And so the name of the game is basically we have to find sort of, for a target logical error rate, what is kind of the optimal layout in terms of the inner surface code distance, so the size of these small squares, the length of one of these blocks, and the height of these blocks, where I hit that target logical error rate, but I have the smallest possible footprint. Now, so I'm going to add one last wrinkle before we get to kind of the conclusion, which is what these actually overhead estimates are. And it's that I've been describing everything in kind of the simplest possible terms using these n-2 codes. And again, it's just we have a sequence of rows of bits and we have some parity bit, right? This is the classical picture. But instead of just checking the rows, I can do something super simple. I could check the rows and the columns. It's a little bit more complicated, but it's not that much more complicated. And here, when I do this, I'm again just using sort of the classical analogy here. Instead of having a distance 2 code, I actually have a distance 4 code, right? Because an error to be missed here would have to have bit flips that are an even number in each row and an even number in each column. And the only way that you can do that is if you have the bit flips being the vertices of some rectangle. So in particular, I need at least 4 bit flips in order to flip some logical information. And the picture looks kind of similar in terms of how I would implement this. So there's some stabilizer code that is an analog of this for the sort of for those of you who are sort of detail-oriented, you'll notice that if I made X and Z stabilizers that were exactly these rows and columns, it wouldn't quite work because they would anti-commute with one another. There's some tricks you can play to kind of get around that. But if I look at sort of the overhead, again, I have now, instead of distance 2 multiplier, I have a distance 4 multiplier. And the overhead, again, is scaling with the perimeter, whereas the number of logical qubits is scaling with the area. And so once again, I've realized sort of this rate 1 scheme where I increase the size of this code. I'm getting, for relatively low overhead, I'm multiplying the distance by 4. So this is kind of the take-home slide. So what are the actual overhead savings when you do this? And the way that we actually estimate this, I want to mention, is by using a combination of sort of path counting formulas and circuit level simulations, because going down to 10 to the minus 18 is sort of infeasible. So that's how we're getting these numbers. And we see really good agreement between the simulations that we can do and the formulas that we can come up with. So with standard circuit level noise in 2D, so everything is 2-dimensional, you just have a square lattice at an error rate of 10 to the minus 3. The x-axis here is the target error rate per logical qubit round you want to hit. So for trillions of operations, you want to be somewhere between 10 to the minus 13 and 10 to the minus 14. And the reason for that is because it takes d error correction rounds to do sort of a logical operation. That's the way we think of it. So 10 to the minus 12, but you want to do like 20 to 30 operations. So this line here is kind of the line we're going to look at. And on the y-axis, we have the physical qubits, including the workspace, the routing, the interstitial space for lattice surgery, all of that per logical qubit. So in blue, we have normal surface codes. And for normal surface codes, we have to go to about distance 23 or so in order to get down to error rates of 1 in a trillion. And that requires a little over 1,000 qubits. So that rejoinder, the surface code costs 1,000 qubits. That's where you would get this from. For these 1D yoked surface codes, which are just checking the rows, we get down to about 600, and it's actually closer to 500. Here, we only use single sig fig estimates, and it's really killing us here. But yeah, so this is going to be basically twice as efficient as these normal surface codes. They also are quite flexible in laying them out in a computation because they can vary quite a lot in sort of the size and dimensions that you use. And finally, for these really densely packed 2D yoked surface codes, where you multiply the distance by 4, we get all the way down to about 350 qubits per logical qubit. So like I said, that rejoinder, it takes 1,000 physical qubits per surface code patch. At least for a memory, that number looks like it could come down to 350 physical qubits per logical. And when we were making these estimates, we were being quite conservative. So I think this number could come down even further. One comment that I'll make is that these logical code blocks are on the order of 100 to 250 logical qubits per block. You want those to be pretty small because you actually want them to fit into a computation. 1D yoked surface codes have a lot more flexibility for this, whereas 2D are a little bit more sort of strict on the requirements. And the intuition, kind of circle back to what I said initially, is that the surface code gets you down to 1 in a million error rates. Don't let the surface code get you from 1 in a million to 1 in a trillion. Let something more efficient do that for you. And so in particular, the logical error correction, these like parity bits, basically logical parity bits, gets you the rest of the way to the 1 in a trillion error rate. It gets you the other factor of a million. So I want to conclude by just mentioning some sort of future directions. The first one is the most obvious one. How does this actually fit into a logical computation, right? This is a memory. There's kind of obvious ways that you can get information into and out of the code blocks using lattice surgery. But how much is this actually going to save you? And there's also a notion of this hierarchy of memory in a CPU, like these different levels of cache memory, for example. And you could kind of imagine different levels of cache memory depending on basically interpolating between how compactly you stored information and how conveniently it was to get that information out of the code blocks. You really need tooling to do these larger logical simulations. We're using path counting formulas, but actually writing down these, you get these giant topological diagrams, and you want to have tools that sort of automatically generate circuits for those topological diagrams. And I think maybe we'll hear more about that later. And also, as I mentioned before, we really, really need fast, scalable computations of these complementary gaps. They're integral to this whole scheme working. And I think you'll hear about that in a paper that's upcoming. And then the final point I want to make is that LDPC codes are very hot right now. They're really exciting, and they give you these really, really big savings in overheads, like a factor of 10 or so, or even more. This is kind of exactly the opposite idea, or at least I kind of think so. This is taking a very non-LDPC code, like an n-2 code, and it's implementing it entirely in 2D, instead of taking an LDPC code with totally non-local or somewhat non-local connections. And as we were kind of building these schemes, we were really using the simplest codes possible. We're just doing parity bits, right? This is kind of the idea. And so a natural question is, like, what are other good small codes with high rate that might push these numbers even further? And something that I was kind of reminded of as we were doing this were these like code tables by Marcus Grassel that maybe some of you have seen before, where he just lists lots of interesting codes up to, like, let's say 30 qubits. And when I was a PhD student, I thought that these were super interesting, but more as kind of a curiosity, because there was no way that I could see where you could kind of build a fault-tolerant scheme out of a random code like that. But when you have something like a surface code underneath, it really enables you to take these one-off codes and really build something useful out of them. And I think that looking over these, doing these small code searches to find these really, really good examples of dense codes and small examples might bring this number down even further. And with that, I'd like to thank you for your attention.
Thank you very much, Mike, for this very fascinating talk. If I may ask one question, you had this discussion of the hook errors, where you said, okay, let's just have this patch very deep. That's so that they don't play a role. But have you thought about whether you could also take logical flag qubits?
No, I haven't. But that is a good idea.
Okay.
I mean, the other thing is, you heard, for example, from Stephen, how for these LDPC codes, like these ancilla patches, were this kind of unfortunate sin where you're sort of giving up all the goodness of the compact memory that you got from the LDPC codes. And the same ideas that might make that more efficient could make sort of this ancilla a bit more efficient. But because you're sharing it, it's a relatively small overhead compared to the rest of the scheme. So there is some opportunity for optimization there, but it's not so bad.
Yeah.
So I have two probably related questions. The first is it useful or even correct to think of this as a kind of code concatenation scheme? And secondly, probably related, like if your logical degrees of freedom are really supposed to be the small surface code blocks, then wouldn't these parity measurements mess with any algorithm that you would hope to run? Like, in general, like you could have arbitrary bit strings, but then each time you do these measurements, you're sort of projecting onto an eigenspace. So how would you use them in an algorithm, I guess?
Yeah, so two really good questions. The answer to your first question is yes, absolutely. This is concatenating surface codes into parity bit codes. To answer your second question, when you do these logical parity measurements, they're commuting with the sort of encoded stabilizers. And so when you do this, you're not going to be messing with the sort of logical lattice surgery operations that are actually implementing your algorithm. However, it is true that you need to be able to get that sort of logical information out of these code blocks when you want. And so if those code blocks are being operated on by these logical parity measurements when you want to do some lattice surgery, it'll have to wait. So I guess what I'm saying is that we've really only thought about this in terms of memory. There doesn't seem like there's any fundamental issue to doing logical operations on these. Specifically to your question, I don't think that the logical parity measurements is going to mess with the logical information that's being implemented by the algorithm. But I will say, I kind of pulled this quote from Craig's paper on factoring, where he mentions that most of the logical qubits in our construction spend most of their time sitting still, waiting for other qubits to be processed. It should be possible to store these qubits in a more compact but less computationally convenient form. And so even if I wasn't able to integrate this with a computation immediately, I just had it as a memory, there's a lot of memory that's required in fault-tolerant algorithms, and so it would just compress that part. But I'm pretty confident that you could interleave them more. Yeah. Oh, sorry.
Oh, I don't know who was next.
So even with the nice reduction for application scale algorithm, you would end up having multiple chips or whatever your substrate is. And so then you're probably having interconnects, photonic interconnects. Do you have a sense as to whether you'd still want to have local, or is there definitely an advantage to highly non-local, or for doing schemes like this? Does this give insight on that?
Yeah, so highly non-local connections are always advantageous if they can be done with the same fidelity as local connections. In the context of sort of this scheme, I think what you're really winning on is that you don't have to have these non-local connections everywhere, where in sort of the scheme that you're describing, you'd have these like photonic interconnects between, presumably not frequently, and you'd have some sort of way of distributing entanglement between different patches at some rate. So I guess this scheme is really aimed at like not taking advantage of non-locality in any way, and it's kind of the strength of it. It doesn't require anything more from the hardware. The deficiency of this scheme is just that the number is worse, right? Like LDPC codes give you sort of a 10x reduction or better, and this is more like a 3x reduction. And maybe we can push it to 5 if someone's clever about doing stuff. But you don't have to build long-range connections, so that's the advantage.
Do you have a comparison of how these numbers look when you're looking at space-time volume instead of just the number of physical qubits?
Yeah, so actually this is kind of a space-time volume metric. I haven't really explained this very well, but on the x-axis, it's the target error per logical qubit round. So on the x-axis, it's a target space-time volume instead of just like a target number of logical qubits.
The y-axis.
Oh, I see. So in there, we're just saying, OK, the time overhead is going to be, think about this. So what this graph is saying is it's saying that if I want to preserve some number of logical qubit rounds, this is the number of qubits that I require. The time overhead that I can kind of imagine coming into play here is like how long the syndrome checks take. And doing those syndrome checks, like the sort of negative of them is that if you want to do a logical operation, the syndrome checks will extend for some amount of time, and you won't be able to do your operation until you get a chance, if those syndrome checks are very long. So we looked at an architecture where we had sort of what we would call like a hot storage, where we targeted basically our logical qubits being available 60% of the time. And there, the overhead is sort of larger. But I think what you're asking for on the y-axis is like a space-time number. And I'm actually not quite sure how to answer that question. We can talk about it later. But we have thought about sort of the time consequences for doing this. So we can talk about it more later.
Right, then in view of time, I would suggest to postpone the rest of the discussion to lunch break. And thanks, Mike, again.
Thanks.